Good day everyone. Today I'll be discussing three important topics in networking: dynamic routing, EIGRP, and EIGRP tuning and troubleshooting. First, we'll talk about dynamic routing, what it is, why we use it, and how it helps routers automatically learn paths in a network. Second, we'll move to EIGRP, which is one of the most efficient routing protocols used in real networks. We'll look at how it works, its features, and some examples to understand it better. Finally, we'll discuss EIGRP tuning and troubleshooting. This part will explain how we can optimize EIGRP performance and how to fix common problems that engineers usually encounter. My goal today is to make these topics easier to understand by using simple explanations and examples. So let's begin. Dynamic routing is a networking method for routers to automatically learn, update, and maintain the routing tables by exchanging information with neighboring routers. This removes the need for manual reconfiguration whenever a change happens in the network. Dynamic routing becomes extremely useful in networks where devices are often added, links fail unexpectedly, or the topology constantly changes, which is almost every real-world enterprise network today. Routing protocols such as RIP, OSPF, and EIGRP allows routers to communicate, evaluate paths based on metrics, and select the best route automatically. This process requires CPU power to compute paths, memory to store routing tables, and bandwidth to exchange updates. However, the benefit is a far more responsive and resilient network. Dynamic routing significantly reduces the workload of network administrators by eliminating the need to manually update routes. When a link between routers goes down, dynamic routing protocols automatically detect the failure and compute a new path, usually within seconds. This increases network uptime and provides built-in redundancy. Dynamic routing is also far more scalable than static routing. A small company with 5 routers may manage static routes easily, but a multinational enterprise with 500 routers requires automation. Dynamic routing also supports multi-path routing, enabling traffic load balancing and optimizing network performance. We categorize routing protocols into three main families. First are distant vector protocols like RIP, which rely on hop count and send their entire routing table periodically. They are simple but slow to converge and inefficient for large networks. Second, link state protocols like OSPF build a detailed map of the entire network and use the shortest path first algorithm to compute the best path. They converge much faster but require more processing power. Finally, we have hybrid protocols such as EIGRP that combine the strengths of both. EIGRP uses the dual algorithm, sends only partial updates, allow extremely fast convergence, and support advanced features like unequal closed load balancing. This makes EIGRP both efficient and highly scalable. Dynamic routing operates through the constant exchange of information between routers. They start by sending hello packets to discover neighbors. Once adjacency is established, routers share routing updates. Whenever a link changes, whether it goes down or a new network appears, the routers update their routing tables based on metrics such as bandwidth, delay, and hop count. For example, if the link between routers A and B suddenly fails, router A immediately notifies its neighbors. Those routers propagate the update, and within seconds the entire network adjusts, selecting the next best available path. Enhanced Interior Gateway Routing Protocols, or EIGRP, is a hybrid routing protocol designed by Cisco. It's highly efficient, supports classless addressing, and runs the dual algorithm, which guarantees loop-free paths and fast convergence. What sets EIGRP apart is its ability to send partial updates instead of full table broadcasts. which reduce unnecessarily network bandwidth usage. It supports advanced features like VLSM route summarization, unequal cost load balancing, and operates seamlessly within IPv4 and IPv6. Its combination of efficiency and flexibility makes EIGRP one of the strongest routing protocols for enterprise networks. EIGRP determines the best path using a composite metric that evaluates multiple factors. By default, it uses the slowest bandwidth along the path and sums the delay of all links. Although load and reliability are available metrics, they are rarely used because they fluctuate too often, which can destabilize routing decisions. Let's say a path has a bandwidth of 100 Mbps and a total delay of 1000 microseconds. After converting this into EIGRP units, the protocol supplies the formula and multiplies the result by 256. This value becomes the metric used to evaluate and compare potential routes. EIGRP communicates using five types of packets. Hello packets are used to find new neighbors. Update packets carry route information and are only sent when changes occur, reducing bandwidth uses. When a router loses a route and lacks an alternative, it sends query packets to ask neighbors for a valid path. Those neighbors respond with reply packets. Acknowledgement packets confirm the successful receipt and critical information. EIGRP uses RTP, its own reliable transport protocol, not TCP or UDP, to ensure guaranteed message delivery. For an adjacency to form, EIGRP routers must agree on several parameters. The most important is the autonomous system number. If two routers have mismatched as numbers, they won't even recognize each other. They must also have matching key values because these determine which metrics are used. Hello and hold timers must also be compatible. If authentication is configured, both sides must share the same hash key. When all these conditions match, routers from adjacency and exchange routing information. EIGRP can be tuned to influence routing behavior. Adjusting interface bandwidth or delay is a common method to manipulate route preference without needing to use static routes. Changing K values allows you to include metrics like load and reliability, but all routers must match or adjacency will fit. Hello and hold timers can be shortened to detect link failures more quickly, useful in critical environments. Route summarization improves stability and reduces routing table sizes. Route filtering allows the control over which networks are advertised or accepted. One powerful feature of EIGRP is its ability to perform unequal cost load balancing. Unlike OSPF, which only supports equal cost paths, EIGRP uses the variance command to include additional feasible paths. For example, the best path has a metric of 1000 and an alternate path has a metric of 1500. Setting a variance of 2 allows both paths to be used because 1500 is less than 1000 multiplied by 2. This increases bandwidth utilization and enhances redundancy. Common EIGRP problems often relate to configuration mismatches. If two routers are different AS numbers or K values, they won't form a neighbor relationship. Another typical issue is forgetting to include the correct network statements, causing the router not to advertise the intended interface. Authentication mismatches also prevent adjacency. MTU mismatch or unidirectional links can cause neighbors to appear unstable. Knowing these common issues dramatically speeds up troubleshooting. The first step in troubleshooting EIGRP is to check neighbor adjacency using showIP EIGRP neighbors. If no neighbors appear, suspect AS mismatches, key-value mismatches, or interface issues. Next, verify the router's configuration with showIP protocols to confirm the correct AS number and network statements. Check interface states using showIP interface with one adjacency is confirmed. Examine the routing table using showIP route EIGRP to see which routes were learned. Debug commands provide live packet information but should be used carefully to avoid CPU overhead.